There's one slight technical detail about line integrals that might have worried you, or might have not, but maybe it should have, which is if we just write down this expression that we've been using for a line integral, integral from a to b of f of r of t times the magnitude of r prime of t dt, right? This is our expression for a scalar line integral. It is not at all clear whether this depends on the parametrization or not. We know that it depends on the curve, but what if you traversed the same curve in a different way? You might zigzag back and forth across it, or you might cross the curve faster or more slowly or backwards, right? So what would do any of those variations change the value that you get from a line integral? So if we use a different parametrization of the curve to calculate this scalar line integral, do we get a different value? So that's a critical question, because it seems like it shouldn't, right? If we have a graph, right, and we calculate a line integral across this curve, we interpreted that as the area of this curtain that hangs down from the graph, and it seems like that should not depend on exactly how you traverse this curve, but just looking at this expression, it's not at all clear why this does not depend on your particular choice of parametrization. So let's reparameterize this integral and see what happens. So what we'll do is, instead of using r, right, r of t, this will be our original parametrization. Okay, so what we need to do is figure out some way of describing how to reparameterize a curve. What we'll do is, let's introduce some new function, which I'll call phi. And phi is a function that goes from real numbers to real numbers. Okay, so just to be concrete, we're going to, let's say that phi is always increasing. All of this will also work if phi is always decreasing, but just to be concrete, let's assume that it's always increasing. So so our original bounds for our line integral for the original parametric curve were, say, from a to b. Well, if phi is increasing, there's some input that gets mapped to a, so let's call that u, and there's some input that gets mapped to b, let's call that v. Okay, and our new parametric curve will be r of phi of t. So this is our new parametrization. So what we need to do is express our line integral in terms of our new parametrization. Okay. So the easy part is the bounds, because the bounds are just going to be from u to v. The hard part is figuring out the derivative of this, right? Because remember, for part of our line integral, we need to know the magnitude of r prime, except it's not r prime, right? What we need is the magnitude of the derivative with respect to time of r of phi of t, right? This is what we get. Okay, so let's write out our parametric curve. Let's parameterize our line integral. It's the integral from u to v of f of r of phi of t, quite a mess, times the magnitude of the derivative of our parametric curve, so ddt of r of phi of t, like so, dt. Okay. And remember, what we're hoping is that this big mess hopefully is equal to the integral from a to b of f of r of t times the magnitude of r prime of t, dt. Right? If these two things are equal, then that is telling us that as long as we're traversing the same path, it doesn't matter at what speed you move along the path. Right? So we really expect these two things to be equal, but if you look at them, they don't appear to be equal. So let's figure out why these are equal. Okay, so this is the integral of u from u to v of f of r of phi of t, okay, times the magnitude of, let's work out this derivative. So the derivative of r of phi of t, this is a composition, so we have to do the chain rule here. So this is, right, r prime of phi of t times phi prime of t. Okay, dt. So this is just the chain rule here. Okay, but now remember that we said that phi is increasing, right? That means that phi prime is always positive, or at least not negative, right? And if we have a scalar multiple inside of our magnitude symbols, like right here, if we have a positive number, a positive scalar inside our magnitude symbols, we can move it outside. So inside our magnitude we have r prime of phi of t times phi prime of t, like this. Okay, now maybe this is the hint that might make you realize how this is going to work out. This phi prime right here, it looks like we're set up for a u substitution. We can't call it u because I've used the symbol u. Let's call it, I don't know, w. So let's say w is phi of t. Then dw is phi prime of t times dt. Okay, and let's adjust our bounds. So what is w when t is u? Well, remember how we chose u and v, right? U was the, I never drew a graph, so here's our graph of phi. U was the input value that got mapped to a, and v was the input value that got mapped to b. So when we're doing this substitution and we need to know what is the w bound that's associated with the t value u, what we get is a. So the bottom bound is a, and then by the same token, what is w when we put b into v, we get b. So our new bounds are from a to b. That's good. Things are looking good. F of r of, now phi of t, that's w. Okay, times the magnitude of r prime of, here, phi of t, that's w. And then right here, phi of t times dt, that's dw. So dw. And of course, this is exactly the line integral for our original parametrization. I've just renamed the variable w instead of t. So we could change it back if we wanted. Right? This is the integral from a to b of f of r of t times the magnitude of r prime of t times dt. Okay, so, and this is the parametrization using our original parametrization r, as opposed to r composed with phi. So what this shows is that, yes, this definition that we've used for our line integral, it genuinely is independent of how we traverse the path, as long as we traverse the path only in one direction. We could traverse it faster or slower, but we will get the same result from this line integral either way. Of course, since this scalar line integral is independent of parametrization, that means our vector line integrals will also be independent of parametrization. Incidentally, the only thing that is different if phi is always decreasing instead of always increasing is these bounds switch because the graph of phi would look like this, so u here and v here, and so it'd be like this. So these bounds switch, but also we get a minus sign when we move phi outside of our magnitude. It picks up a minus sign there, and those two minus signs will undo each other, and so we do end up getting the same thing.